This is a talk about a line of work I've been pursuing in the last few years, and I found it very interesting and fascinating. Is a collaboration of a bunch of people, including PhD students, postdocs, and faculty like Ishai, Claire, and Massi Pontil. The main teams that are involved in this line of research is the main team is that of learning agents on a communicating network. And I will make the setting quite precise. It's a setting that is amenable of theoretical investigation. We are interested in improving theorems on how cooperation can help agenting learning faster when they are on a communication network. And we will frame this question in a very precise and theoretically grounded way. And one thing that was my motivating, my main motivation is, which I found very nice, is the investigation of how learning algorithms that interact with each other will co-evolve, will modify the learning trajectories in order, accounting for their interaction. And another thing I will be studying will be mentioning also the fact that once there is communication, there could be delays. And so a side theme in the impact of delayed feedback on the learning performance. Okay. So let me give you a few motivating examples why we should study these networks of interacting learning agents. We have by now larger scale geographically distributed learning systems that do different tasks, maybe finance, recommendation, advertising. These are possible examples of these larger scale networks. And we also have networks of different nature, like mobile sensor networks. For instance, they do environmental monitoring, and they need to have a common task, and they can use communication to perform the task more efficiently. And in many cases, for instance, think of finance. We have a high rate of predictions. And in other cases, like the mobile networks, we have energy requirements. So in many cases, there are some constraints on communication. And for instance, we might want to limit communication to the some kind of neighborhood in our network. So this will be one of this. We will be looking at different trade-offs in our analysis, and this will be one of the trade-offs we'll be looking at. Trade-off between speed of learning and how far away we can broadcast information. We will cast our investigation in the framework of online learning, because this is something I know well, so I can say something possibly interesting. And this is it's a kind of I would say is a nice fit with the previous slide, because data streams are common in markets, financial markets, in sensors, in user interactions, which arises when you are recommending items or content. And online algorithms are particularly efficient when they are designed to operate on streams, and they will operate on streams by incrementally adjusting their models as new data points from the stream are being revealed. So there's no training testing dichotomy as in standard statistical learning, but there is an incremental learning with small adjustment to an evolving model. So this is why the theme of co-evolution is appearing here, because these algorithms, the models will follow some trajectory in the model space, and whenever these algorithms are interacting, the trajectories will be somehow correlated. And the trajectory is caused by the fact that the stream is being fed to the algorithms, okay, the data stream. And another nice feature of online analysis is that typically these analyses are very robust to the specific mechanism that is generating the data stream. So we won't be making, typically we won't make stochastic assumptions on the way the data are generated, okay? Which is something reasonable if you want to tackle problems where streams are not stationary, okay? Cool. So let's look at more in detail at our protocol for online learning on a network. First of all, we are fixing some model space or decision space. You can do it in both ways, which will be some subset of the d-dimensional Euclidean space. So our models will be parametric models with d-many parameters, real-valued parameters. And we will have a network of agents. Each agent is sitting on a node of this network. And we were looking at the protocol in which at any time step, some agent is called on duty, becomes active, must make a prediction. Okay, so an external entity is requesting a prediction to that specific agent for some reason. So the agent will predict using its current model. So VT is the active agent at time t, and XT of VT is the current model that the agent will be using at time t to make its prediction. And the prediction will incur some loss, which is L sub t of XT of VT. For instance, we may assume that this loss is the square loss on a certain data point. So I'm hiding data points here. The data points are somehow absorbed into the loss notation. So you can imagine that we make some if you want linear regression on a data point pair. We are looking at some data point. We are making a linear prediction. We are recurring square loss, and afterwards we'll be given the true label. Okay, so the agent, once the agent gets the label, can update its model, and then it will share the label, or more in general, the feedback information, whatever this is, to the other agents, maybe just the neighbors in the network, who may also use this information to update their own models. Okay. So this is basically our general abstract setting. So you should think of losses as convex loss functions like square loss, absolute loss, hinge loss, anything that is convex. And the problems can be classification, regression, whatever you like, okay? Or more abstract problems. Okay, so in online learning, we are looking at the specific, so there is no statistical risk here, because the data stream is completely deterministic, arbitrary. There is no IID generation of data. So we are looking at a specific way of defining risk. So first of all, we are looking at for any point of time, capital T, we are looking at the best global model so far. So on the entire stream, which is represented by the sequence of loss functions, which also incorporate the data points and the labels, we are looking at the model in the model space, which is minimizing the sum of the losses. Okay, so there is no expectation here, because it's this individual sequence of data points which induce these losses. So we are looking at the best model which minimizes all the losses in the stream so far. Okay, but now we are looking at something. So remember in the previous slide that the stream is split across the different nodes. Every node observes a subset of the stream because it only directly observes and pays the loss for the point of the stream for which it was active. Okay, all right. So we now define the regret as the sum of the losses of the active of the model of the active agents. All right, that's the LT of XT of DT minus the sum of the losses of the best global model. Okay, so now you should think of these bunch of agents. They don't know the stream, the data stream they're facing. They would like to compete against the best global model, but they are looking. Each of them is looking at a subset of the stream, and they are communicating feedback information with each other in order to somehow learn faster. Okay, so let me make a little bit more sense of this model. Okay, first of all, okay, how do I detect that some learning is happening? If I assume that loss is bounded, which is typically the case if the learning domain is bounded and the instance domain is bounded, if the model domain is, let's say, the model space is bounded, then everything is bounded, losses will be bounded. The instantaneous regret at any point of time can be at most bounded, the constant, some constant. So if I just predict a random, my regret can grow at most linearly with time because it's a sum of constant pieces. Okay, so I would say that I learn if I'm able to control my regret to force him to grow sublinearly. And this implies a convergence to the average loss of the best global model. You may say, okay, but maybe my regret can grow even can get even negative. Yes, in certain cases it could also grow negative, but remember that we are looking at in arbitrary sequences of data. So for the worst case choice of the data sequence, my regret will be always positive and will grow at a certain rate. Okay. So what is known? Okay, I can assume something very very basic now. Let's assume that always the same agent is active. So now, okay, only one agent is responsible for making prediction, and he's observing the entire stream because it's him, always active. All right. So then we are back in what I would say, what we call a single agent online learning. There's one agent making prediction on the entire stream, and the agent is competing with the best global model for the stream. So now the online learning literature will tell you that the regret will grow as the square root of time. Okay, and this implies that we converge to the average loss of the best model at rate 1 over square root of t. This is our learning rate, if you like, in this online learning model. And this holds for any convex losses, provided there's some boundedness condition and blah, 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 blah. Okay, so there are some hidden parameters in the big O notation here, which is the diameter of the model space, the Lipschitz constant of the loss, but we don't care about these details now. For now, what we care about is the dependence on time. Okay, so now we may wonder, what if okay, this is, by the way, this rate is achieved by several algorithms, like online mirror descent and follow the regularized leaders. These algorithms will use loss gradients to update their models. So morally, they perform gradient descent, but in an online way. So they do it on the data stream, not on a fixed data set. Okay, the data is coming up one by one, and we do online gradient descent on the fly on this data stream. And we can prove this bound on the regret, believe it or not, for any data stream. And we can also prove that this rate square root of t is the best possible. So it's not improvable in general. In particular, if the loss is linear, like absolute loss, then I can design a stream on which any online algorithm will have this much regret. So I cannot converge to the best model any faster than 1 square root of t unless I have special properties of the loss. Okay, So now this is basically the background. So we are now looking at the network thing. So let's start with something very simple. Let's assume the agents don't talk to each other. They don't want to exchange information. And then what happens? We can still apply the analysis we had on the previous slide. And okay, this is basically the only derivation I will be showing in the entire lecture. So, right, let's assume we have n agents. So every agent will be active for a subset of the stream. Let's say that the agent V is active for a number of time steps, which is T sub D. So now we saw before that the regret over that time span will be the square root of the number of time steps on which the agent is active. So we can sum up these regrets, since at every time step only one agent is active. And then we can multiply and divide by the number of agents and use Jensen's inequality. And we end up with the bound, which is because sum over V of TV is capital T. We end up with this bound. So we now see that if we run our online mirror descent with the bound we saw before, and on a network, any network, the agents don't talk to each other, we have a bound that scales with the square root of the number of agents. So we can, you know, if you like, you can say that this is the price that the agents pay because they ignore communication. Okay. So now, and this is tight when the communication graph has no edges, and basically every agent is active for the same amount proportion of time steps. So if the agent cannot communicate because the communication graph is empty, then this is the best they can do. But what if there are edges on the communication graph? What if they can actually communicate? How can this? How much can this help? Okay, so this is a question, and we can easily, with a little bit of thought, come up with the lower bound. And the lower bound is of this form. Let's assume that I will activate only, so this is the communication graph for the agents, and let's assume that only the red agents get activated, and let's assume that agents can only talk to their first neighbors. Okay, so now the first neighbors of the red agents are the white nodes, and they are never active. They do nothing. Okay. The information is not passed on past the first neighborhood. So in this case, it's like the agents are back to no communication style. They're back in isolation. They learn independently because they can only communicate to their first neighbor, but their first neighbor never participate in the prediction game. They don't do any prediction. So now, how many red agents can I have on a graph? Well, I can have an independence number of agents. So the independence number is exactly the largest cardinality of a subset of vertices in a graph that are pairwise non-adjacent. Okay, so they don't share neighbors. So they're not neighbors, sorry, they're not neighbors with each other. Okay, now my problem, you can see it is as if I were playing a game in which I have alpha many agents that don't talk to each other, and I already know the rate for that. That rate is exactly square root of number of agents times t because of the derivation I had before. So this is a lower bound. And this lower bound will depend on this independence number, which is a structural constant of the graph, which is 1 in a clique, because in a clique if is a neighbor of each other, and is equal to the number of agents in a graph with no agents when no communication is possible, because if I have no agents, then nobody is a neighbor to anybody else. Okay, so now we have a reasonable lower bound. You know, if I bound the communication, then definitely I can make the agents feel isolated. And then we won't be able to learn any faster than that rate. Now the question is, can I actually achieve that rate with some algorithm? And all right, so I will show you if I will show you that if the agents are stochastically activated, this is possible. This rate is possible to achieve. So now I'm assuming that agents are activated at random IID from some unknown distribution, and each agent will run the algorithm as before, the online mirror descent, this standard workhorse of online learning, and the algorithms will share their feedback information, which is in the case is the gradient of the loss. They will share it because OMD uses the gradient, as I said before. They will share it with the neighbors, which can update their models, uses this feedback information. And it's not extremely hard. It's actually not so hard to prove that by doing this independently of the distribution from which the active agents are drawn, provided that the distribution is fixed, okay, over time, I can achieve this result. And this is even true when the agents completely ignore the topology of the network. In other words, the agents can be initialized, the instances of online mirror descent can be initialized irrespective to the position of the agents on the network. And the agents don't have to know anything about the network. Okay, so when the network is a click, alpha equals 1, and we recover the single agent bound, because now it's like there's only one effective state in this network. Because if I'm in a click and I share with my neighbors, then everybody knows everything. And when the network has no agents, no edges, then there's no point in sharing information because I have no neighbors, and I get back to the no communication bound because alpha equals n. So this is a kind of a bound tight throughout the spectrum of connectivity for the graphs. Okay, good. So now, okay, this is good news. I can see that this arbitrary activation gives me a nice way of, a nice lens through which I can measure this power of communication with neighborhoods, sharing gradient information with neighborhoods. And this is exactly dictated by this independence number of the graph, which is a clear structural parameter. So now what happens if I say, no, wait a minute. It's too optimistic. In my problem, I have some activation schedule that depends on the location of the agents in the mobile network. There's some environment, it's a mess. I cannot assume IID. So what's going on? All right, I try to use the same algorithm as before, but no worry, I will use the same strategy. Wait a minute, I get a linear regret lower bound here. So if I try to use the same strategy as before, I can come up with networks like this one, like a star, in which I basically, the network regret will be linear. There is no learning at all. Nobody is learning. Somehow I can do this. This is kind of mesmerizing if you look at the center of this star graph. Okay, basically, I can make the center of the star believe that the best prediction is a different one from the actual best prediction. And now this guy will spread, is a sort of an influencer in the network, and will spread fake news. And all the others will believe him and make updates that are completely misleading. So I can amplify a little bit, by injecting a little bit of fake news, I can have that amplified. Sounds familiar, right? And at this point, it's better if we don't talk to each other. If I am sensitive to fake news, it's better that I don't talk to my friends. All right, so is there any fix? And this is actually interesting now, because my upper bound for stochastic activation assumed that I didn't know anything. My algorithms were completely blind to any information about the topology of the network. But maybe this is a bit too harsh. What if I let them know, what the network is like and where they are? Okay, then it's kind of easy, because somehow they can organize, they can group themselves in clique. And once they group themselves in clique, they can sort of share information with each other in a clique. in this case, because the click is completely symmetrical, there is no this amplification phenomenon anymore, and things go back to normal. So now the effective state of the network will be the click covering number, the smallest number of clicks with which I can cover my network. This is going to be the ruling parameter of my regret. And I can even get a little bit better if agent can also share their entire models. Like not only I share my gradient, my loss gradient, but I actually can upload my models to my neighbors. Then I can get something a little bit better than click covering, actually much better than click covering. This is the domination number of the network. I'm not dwelling on these things, but just to know that the domination number is even better than the independence number, whereas the click number is worse than the independence number. So basically, if the agents know the topology and their position on the network, and they can share a lot of information, they can entirely share their models, they can even be protected against arbitrary activation sequences. Oh, I already have questions. Maybe since I'm not done yet, I will answer a little bit later. Okay, and then we'll come back to questions. Right. So now let's see. We have other learning models, like, for instance, one way of considering online learning is by restricting the amount of feedback that you can share with your neighbors. And this is called the bandit problem. In the bandit problem, you cannot share the entire gradient of the loss. So in an abstract way, let me phrase it like this, and then I will relate it to the previous setting. So I have k actions like k musical genre, and I have a known assignment of losses to actions for each time step. And you can think of it as a linear loss, with a k-dimensional linear loss, if you like. And every time step, an agent will pick an action, possibly using randomization, and will incur the loss associated with that action. So maybe I will recommend a certain song from a certain genre, and you will tell me if you like it or not. And then I will find out the loss value, but only find out the loss value for the particular song I recommended to you. Not for, I don't know the entire loss vector. I only know one component of the loss vector, the one I predicted. All right, these are lots of applications. You might have heard of it. So add placement, real-time bidding, and many recommender system, of course, and many others. All right, so what happens if I try to use the same idea that I told you for on bandits? Now learning is harder. And in the single agent case, okay, we can solve this problem by running a randomized variant of online mirror descent in a decision space, which is the k-simplex, and the losses will be linear losses. Linear losses because it's like here, it's like my loss is linear, and okay, I'm paying the component of the loss I am playing. It's an expectation with respect to my randomized choice. I will have a linear loss, which is a convex combination of the probability with which I chose my prediction, my action. Okay, it's a special case of what we saw before, and I need to use a little bit of randomization in order to compensate for the missing information. Okay, so morally, it is like in this case, every agent only observes a component of the loss gradient and can only share that component of the loss gradient to the other neighbors, because I only know the loss for the song I recommended, not for the songs I did not recommend on that time step. So the single agent regret now will scale with the number of actions. So with the dimensionality of the problem in this case. So there is this additional parameter that pops up that has this dependence on k, all right? And now I can see what happens if I do the same game? So now, since I have low linear losses and I'm working on a simplex, my best global model will be always a corner of the simplex. That's fine, just to be concrete. So I'm competing with the corner of the k-simplex with the best model in my space. The regret has the same definition as before. And I can basically prove something very similar to what we had before. If I run my variant of online mirror descent without communication, I will have a dependence that scales with the square root of the number of agents. If I use communication and I want to be able to exchange gradients, I will exchange the gradient components. Okay, I will still have a dependence on the independence number of the communication graph. Okay, and I have this additional dependence on k. Cool. This thing can be run, and the red line is the regret if you don't use cooperation, and the blue line is the regret if you do use cooperation. So if you run this algorithm on real problems, so this is actually a synthetic problem, but you will actually see these differences for real. Okay, cool. Now, what about delays? So let me say something about delays. So this delay is pretty natural because I can now assume that why should I stop to the first neighborhood? What if I broadcast my feedback information through the network? Okay, first neighborhood, second neighborhood, third neighborhood, until up until the diameter of the graph. And now I can assume that every inactive agent will receive the feedback information from the active agent with a delay equal to the shortest path distance from the active agent. Imagine a nice drawing. I didn't do the drawing, but you can imagine it. And we can, in order to bound communication cost, because this broadcast is costing me a lot of messages, I assume that messages older than d time steps are discarded. So I have a time to live for my messages. So now there is an interesting trade-off coming up here. So now the regret in the full information case will depend on alpha d, which is still an independence number, but I will tell you a little bit more, plus d, where d is this maximum delay I will tolerate. Okay, and in the bandit case, as you can imagine, instead of alpha, I will have k alpha, but it's pretty much the same thing. So what is alpha d? So alpha d, you can guess it, is the independence number of the dth power of the communication graph. So this is as if now I can communicate not only with the first neighborhood, but I can communicate with any neighborhood up to the dth neighborhood. So is as if I did a transitive closure of all the neighborhoods up to d distance. Okay, so clearly, if d grows, alpha d shrinks because I'm adding edges to the communication graph, because I can talk to any neighborhood up to the dth degree neighborhood. And if the graph is dense, alpha d will shrink faster as d increases. So now in the regret, d goes up and alpha d goes down. I have a trade-off I can try to address. So let's see how I can address this trade-off. Let's focus on the full information case for concreteness. So by increasing the delay bound, I increase the quantity of feedback information an agent receives. Because an agent is in the dth neighborhood of an active agent will receive the feedback of that agent after a delay of d, right? If I increase d, more agent will receive the feedback of any active agent. However, as we saw, delaying updates slow down learning, because if I use a stale update, I pay this in the regret. You see the square root of d term in the regret. The d term in the square root function of the regret. So now I would like to increase d, but not by too much. And so one way is kind of easy and is kind of rough, but it gives you an idea. So it's not too hard to prove that on any connected graph with n nodes, alpha d is at most roughly n over d. Okay, this is not too hard. It's a standard sort of a result that is known in graph theory. It's not very hard to prove. And so if I choose d or the order of square root of n, provided actually the minimum between the diameter of the graph and square root of n, this by putting this choice of d back in my bound and using the upper bound for alpha d, I get a regret of the order of n to the 1/4 square root of t, which is always better than the no communication bound. So this is telling me that, you know, if I know that I might be able, I know that alpha d is smaller than n, but I don't know by how much. However, if I use this trick and if I use this specific choice of the delay, I can actually obtain a strict improvement over the no communication bound I had before for the agents that do not communicate with each other. Right. Okay. Cool. So now let's move to the last topic. Okay. So here in this setting, I slipped something to you. Some of you might have noticed it. So, you know, okay, first of all, I can rewrite my network regret as the following. I'm competing, you know, on the left-hand side, I have this sum of, on the first sum is the sum of the losses of the active agents. And the right-hand sum is the sum of the losses of the best global model. Now you may say, okay, wait a minute. If I have agents on the network, why should I actually compete with the best global model? Competing with the best global model in the sense it means that all the agents are solving the same problem. So they are learning on the same stream, although each of them sees a subset of the stream, because that depends on the activation sequence. So the regret does not depend on, okay, the benchmark on the regret, the best global model does not depend on the activation sequence. However, my performance will depend on the activation sequence. So now I can say, let's take a more general viewpoint. I don't want to compete with the best global model given the stream, but I want to compete with the set of best local models, given the way the stream is split across the network depending on the activation sequence. So every agent is going to be active on certain time steps, is going to be observing a certain sub-sequence of the stream. And now I'm looking at the best model for that specific subsequence. And now I want each agent to compete with its own best local model. Now it's much, much harder, the problem, right? Because each agent is competing with its local model. The other agents have different benchmarks, but they still want to use communication. Why they should use communication? What is the only reason why they should use communication here? The only reason why I should use communication, right, is whenever these best local models are kind of similar to each other. So if I'm learning a certain task and my neighbor is learning a task which is similar to mine, then it makes sense that we should share information, because our tasks are pretty much the same. Maybe not exactly the same, but similar enough. So now the question is, to what extent the two tasks should be deemed to be similar in order for two agents to have some benefit by sharing information? So that's the question. So the last question I'm going to ask here. I have 6 more minutes, right? Okay. So let's go back in the single task case, multi-agent. Now we can call it single task because before we were competing with the best global model, and we saw that with respect, if we had the stochastic activation with respect to the no communication case, no agent is talking to each other, we could improve by replacing the number of agents with the independence number of the communication network. That is cool because alpha is always smaller than n, and we saw examples where this can be actually always better. Right. So what are we gonna show? And this is like a spoiler. In the multitask multi-agent case, when everybody is competing with the best local model, we're gonna show that the square root of n is gonna be replaced by the square root of that expression. And we are actually going to be able to prove that even for the deterministic activations. So we are not using the stochasticity. Or to put it better, I don't know how to use the stochasticity. All right. So what is sigma squared? Sigma squared, okay, it's something that makes a lot of sense. Is the variance over the set of best local models. So remember, local models are vectors of coefficients because we are in a parametric case, so they are points in the space, in the d-dimensional Euclidean space. So I'm now look for, given a stream and a bunch of agents and the sequence of activations, this is defining a set of local models that are the best model for that particular splitting of the stream over the set of agents. And now I can look at the spatial variance, actually the variance, right, of this model in the model space. And I call that sigma squared. And if sigma squared is smaller than 1, then that quantity is actually, right. Now this quantity is actually better than the, yeah, you see the left-hand side of the yellow stuff is better than the right, smaller than the right-hand side of the yellow stuff whenever sigma is more than 1. So in other words, when the variance is small enough, and this is the threshold, it's convenient for the agents to exchange information. And in this case, I'm not assuming, so this is sort of a simplified because I have a very little time left. This is a simplified view. So I'm assuming agents are on a click and they broadcast information to each other. And so an agent is receiving the gradient of another agent. It doesn't trust completely the gradient. So it won't use this gradient to make an update of its model, but it will use a scaled version of the gradient. And the scaled version will be with a scaling factor, which will be chosen as a function of sigma squared. Okay, right? So the agent will know something about the variance, otherwise they don't know if it's convenient for them to exchange information or not. And if they know some bound on the variance, and they will use this bound in order to scale the updates and get that, and then get that gain, and that gain is actually the best they can get. So it's impossible for any algorithm to gain anything better than that by exchanging information in this setting, in this multitask setting. A kind of a nice lower bound. Again, we can run these things. So now here we have losses plotted on the y and time on the x. And the blue line is our multitask online gradient descent, which is a version of online mirror descent. And the red is the independent, no communication, and the green is like a single agent. So I'm trying to solve a multitask problem using a single algorithm. Okay, so a single, right. So I'm sort of learning the centroid of all the models, or of all the best local models. Okay, and actually there is a little bit of thing here, very little. So the notion of variance is actually matched to the geometry of the model space. So if I work if my model space is Euclidean ball, I will use the standard Euclidean variance. If my model space is the simplex, because I want to predict probabilities, then my notion of variance will be tailored to the simplex. So that's a kind of a subtle important point that the bound will hold irrespective of the geometry of the model space, but the notion of variance will reflect the geometry of the model space. All right. conclusions, 1 minute left, maybe not, maybe a few more. No, just one. Yeah, so we quantify the power of communication in single task multi-agent learning. We saw that we could trade off delay with the amount of feedback information. We saw that our analysis can transfer to bandit setting. And we also found a way of expressing the power of communication in the multitask multi-agent online learning case. There is a bit of work that is work in progress. So what we are after is a single algorithm and analysis that sort of encompasses both the full information and the banding setting that as of now use different algorithms. And this will include a bunch of intermediate cases known as a feedback graph model in just one nice result that completely interpolates between full information and bandits. And this is still work in progress with Tom and Riccardo Della Vecchia. Okay, thanks a lot. This is some references for you if you care about reading, and thanks a lot for your attention and patience.
Thank you, Nicolò. Very, very nice and well dense talk, I would say, from this point of view. I see there are a few questions on the internet.
Yeah.
So first, well, maybe we can let Daniel ask directly his questions. I see that he has like 2 questions. Daniel Romero. If not, I can read the question. So he's talking about well, some proof for the technique on slide number 9. I don't know exactly what. Maybe you can go there.
Well, first of all, yeah, technique on slide number 9. Oops. Yeah, I think it was the very first result, and. Oh, yeah, okay. Yeah, the analysis here is somehow, okay, what is the proof technique? It's actually super easy. It will be in the reference, in the second reference I gave in the last slide. Mm-hmm. And it's essentially, okay, you should think of it. I am an agent. Sometimes I'm active, and whenever I'm active, I make a prediction and I pay for it. Sometimes I'm non-active, so I will receive a free feedback from if I'm a neighbor of an active agent, so I can make a free update. So now you can sort of measure, you can look at a regret as a more general, let's say, pseudo regret, which is a sum of updates that are not paid for and updates that are paid for. And now, paid or non-paid, depends on whether I'm a neighbor of an active agent or not, or I am myself active. Since activation is stochastic, there is a nice graph theoretic trick that allows you to pull out the independence number using the stochasticity of activation, because this has to do with the neighborhood, the structure of the graph.
Right.
Okay. So the second question is interesting. Okay, it seems strange that the first claim holds depending on whether sigma 2 is greater than or equal to 1, because that makes, okay, there's a notion of normalization here. So there is some hidden normalization.
Yeah.
So I'm looking at, I didn't tell you about the decision space. So the decision space will have a diameter which depends on sigma squared. So that's the reason why. Very nice question. So you got me. You got me. Agents will know sigma, or will know an upper bound of sigma, and then we'll use this upper bound of sigma to somehow rescale their decision space. Very nice. Thanks. Said, yeah. 1xp3 as also he caught me here as an extra log k factor in the regret. Why this factor doesn't appear in your bound? Well, there are a little bit more sophisticated version of xp3 that are not called xp3. You're right, but the log k factor you can shave it off if you want. Otherwise, you put a tilde in my big O notations. Yeah, but it was a little bit imprecise. So I said xp3, but I didn't mention the log k. Yeah, you're right. You can either put the log k, use xp3, or use a more complicated algorithm, but the analysis will still hold and shave off the log k. Thanks, you got me. All right. Let's see, Tarek. in the multi-agent setting, if we share a perturbed version of the losses in the bandit setting, then, oh, wait a minute, I have to wrap my head around this question. We share a perturbed version of the losses in the bandit setting. Okay, yes, in the sense, so this is a pretty much, so, right, you mean perturbed because, why perturbed? Because I am in the bandit setting or for other reasons? I don't understand.
Yeah, Tariq, if you want, you can explain your question.
I don't fully understand why you say bandit and perturbed. You mean additional perturbation just because I am in a bandit setting, I only say component of my...
Yes, and I guess this is what he means, and he's asking if you have an extra clause for this.
Yeah, okay. Right. It's basically, yeah. You have to combine the bandit analysis with the full information analysis I was explaining to Daniel a moment before. So, yeah, it's a little bit tricky to make things go through both for bandits and full information. And but it is possible. There are two techniques. One deals with the fact that I have these perturbed losses, and one deals with the fact that I have stochastic activations and the spread of information with this sort of pseudo regret I was mentioning before. Mm-hmm. If you put these two things together, then you can actually analyze bandits in pretty much the same way. But yes, the fact that you have loss estimates is requires an additional technical step. So it's not an easy variation.
Okay.
If activations are deterministic, is there any lower bound for this case? We don't know of a general lower bound for, yeah, we don't know whether the, the dominating number or the domination number is the best possible. We don't know that, absolutely. We have no idea. Mm-hmm. How are the rates robust to the strategic behavior of the agents? No, this is a very nice question. So what if agents are strategic? So maybe we have some defectors, maybe we have some malicious guys that are actually not sharing gradients, but sharing something. Yeah, they don't want to compute the gradients. They just share some random stuff. This is a super interesting questions. This has a lot to do with federated learning and this kind of models, and there's very little known about it. Yes. Yeah, I don't know. Very, very interesting.
Okay, he's talking about some. There is Yassin Hamdi. Yassin is talking about the hypothesis of the you are putting, but I think you already answered about. I mean,
yeah, losses have to be convex because that's exactly the online learning business. And full info or bandit info, yeah, we covered everything.
Okay, and then there is a last question from Adan Gomez.
Is there some relation between learning algorithm of each agent, its learning speed and spread information speed? Have you made some experiments where each agent can have a different type of learning algorithm? No. Okay. We don't know. I mean, no, we were so happy that we could deal with the same algorithm replicated. You are saying that, maybe if I'm on a high degree node, I should use a different algorithm or maybe a different initialization or maybe a different learning rate. These are all great questions. From the one hand, you would like to be as much insensitive as possible to the location of the algorithm on the network. It's kind of useful to deploy the same instance with the same initialization throughout the network, if you think from an engineering viewpoint. But then if you have additional information, that would be also useful. We don't know how to do this. No. Our analysis is completely blind to these aspects.
Yes, I assume he is talking about some kind of heterogeneous network in which you can have some sort of, different type of agents having different goals, different structure, and maybe there you could probably, if you can in a simpler way, you can think of like I have a higher degree, I can learn faster. Yeah. So my learning rate can be a little bit different from, because I've lots of neighbors, so I'm learning faster. Yeah,
there's also, again, there is some little work about it, but very little, and only for certain limited cases. These are all wonderful questions. I mean, there are not a lot more than these three papers. Sorry, this is not. These are the papers. 3 papers and few more papers that talk about these models. People, of course, talk about distributed learning, but in a different context. I like online learning because it allows you to bring out these trade-offs in a very crisp way. And I think they are kind of easy to understand. Okay, and that's the reason why I do online learning. But you can study these things in statistical learning, you know, federated learning with privacy and stuff. And yeah.
Probably in a simulation environment, probably you can also show that this can work in some sense. Maybe in real life it's more difficult to model it unless you really have information about it.
Yeah. So we didn't play on. We tried this with different geometries. We tried this with you know, simplex Euclidean spaces, but these are toy experiments,
right.
And these are actually real data. This is a Lenk data set, which is a standard data set for multitask. But this is more theoretical. This is as for now, this is purely theoretical work. So this is sort of supporting our theoretical results, but we don't know a lot. We don't know about engineering in real cases, these things.
Okay. Any last questions? Well, if not, well, thanks a lot, Nicolò. I think it was very, very interesting. I think it's, as you mentioned, I think it has a lot of applications, and so it is a theoretical proof. But as you said, it's quite has a good connection to practice, and that's something useful to many of us. So that's definitely very, very interesting and useful. I see that many people are thanking you for your responses and for the great talk. So really,
thank you so much, Nico. Thanks a lot.
Thanks a lot.
It's been a pleasure.